All right. So hello, everyone. We are very happy to have today Professor Hamid Hassani from the neighborhood, actually, but still over Zoom from UPenn. I met Hamid some 14, 15 years ago when I was on sabbatical at EPFL, and he was just a beginning student at EPFL at that time. And even then, he was a star student. And since then, he got all sorts of awards. He got a dissertation award from Information Theory Society and a paper award from Information Theory Society, I believe, and then career award, etc. And he's an excellent speaker, so we are definitely up for a treat. And recently, he has been appointed to serve as a distinguished lecturer of the Information Theory Society, and that's probably the youngest person I know ever appointed for that role. So without further ado, let's
all right. Thanks, Amina, for the introduction, also for inviting me, and thanks everyone for attending the talk. So the talk will be about learning robust models, and I'd like to start with saying a few words about some of the applications where robust models are important for. And these are safety critical applications. So here, by safety critical, I mean any application where the detections, decisions, and recommendations made in those applications would directly impact the safety of humans and the well-being of humans. A canonical example would be self-driving cars, where detecting, let's say, pedestrians in a sidewalk would impact the well-being of those pedestrians. There are, of course, many other applications and domains, such as robotics, as well as medical imaging, where the interaction. Yeah.
I think your slides are somehow not working, so I don't know if the screen sharing is sharing. Sometimes you have to share like this. I think you have to share the full screen, and I don't know if you go into full screen mode, what happens. Anybody know? I never actually figured this out.
Yeah, let me go to the full screen, and then the whole desktop.
Correct when you first tried.
Let's see. Is it working now?
Yes.
Yeah. That's
okay.
Working great.
So
thanks,
yeah, so a canonical example of safety critical applications is autonomous vehicles, where detecting, let's say, pedestrians in a sidewalk would directly impact the safety of those pedestrians. There are, of course, other examples and domains and applications, such as robotics, as well as medical imaging, where the interaction between, let's say, robots or learning-based medical systems and humans are subject to obvious safety critical constraints. So the main message here is that machine learning systems, when deployed in safety critical applications, must be robust and trustworthy. Let me now say a few words about this term robustness here and how we mathematically and geometrically think about it and formulate it. When talking about robustness, a natural starting point would be to talk about the phenomenon of adversarial examples. I'm sure most of you are familiar with this phenomenon. Let me quickly review it and maybe talk about some of the notation that we're going to use later. So let me start with simple supervised learning. In simple supervised learning, for example, deep learning, we have a data set. We train a model, for example, a classifier for a specific classification task that we have on the data set. So we start with some standard data set and we train a model. Now, the success of supervised learning or deep learning typically implies that when the model is used to classify newly unseen test images that come from the same domain as the training data, then the model would classify, for example, this image here with high confidence and high probability. Okay, so if I have seen a few pictures of panda during training time, then most probably at test time, if a new image of a panda comes, then my model would be able to classify it correctly and with high confidence. So that's just the success of deep learning. Now, adversarial examples could be explained as follows. Let's take the same image and assume that we add to it a very small amount of noise in the following way. First of all, so the noise is very small, or in other words, the perturbed version of the image is indistinguishable to us as humans with respect to the original image. And also, typically, the choice of the noise can be made in a way that the perturbed image is misclassified by the model that we are using. Of course, the choice of the noise here should be well crafted with respect to the model that we are using, as well as the data point. Or in other words, the choice of the noise is adversarial. But what's important here is that adding a small amount of noise can cause misclassification, as you see here. Let's dig a bit more into these phenomenon of adversarial examples. Typically, in machine learning, we represent data points as some points or vectors in some Euclidean space. Now, around each data point, assume that we draw a ball of radius epsilon. Think of epsilon to be a very small number. Within this ball, we typically search for a perturbed version of the image, such that the perturbed version would be misclassified by the model that we are using. And this perturbed version would be called an adversarial example. Now, in order to find the adversarial example, we have to search through the ball and find the worst case point, basically. But again, the message here is that adding small amounts of noise can cause misclassification, or our modern deep learning systems are highly fragile with respect to these kind of norm-bounded perturbations. And this phenomenon is now well documented within this area of machine learning. There are now thousands of papers that talk about different properties of adversarial examples. They propose different algorithms to make our models robust against these examples, and so on and so forth. Along the literature, most of the literature so far has focused on two very simple geometries of perturbations that are allowed for to find adversarial examples. The first geometry is the so-called L2 ball, which is essentially the typical Euclidean ball. So around each data point X, you draw a ball of radius epsilon. Within this ball, you're looking for, let's say, the worst case input that causes misclassification, let's say. Another geometry that people have studied a lot is the so-called L infinity geometry. It's again the L infinity ball of radius epsilon. Now, most of the literature has focused on these two geometries because they are very simple. We know what the geometries are. We can optimize, we can essentially search through these balls easily to find the worst case point, and so on and so forth. But nevertheless, there are many other geometries for safety critical applications that are as important, if not more important, than adversarial examples or norm-bounded perturbations. So, for example, you may have heard about adversarial patches on the right, if you see here. So you add small patches on a stop sign, and that can cause misclassification. There are changes in background color, darkness, like light, or even changes in the weather conditions that can cause misclassification. So, for example, on the plot that you see on the at the bottom, so the test accuracy of a famous neural net-based classifier quickly drops as the amount of snow in the image increases. Okay, so like number 4 on the x-axis is like heavy snow. Number 3 is like slightly lighter, and so on. And number 1 is essentially when there is no snow. So when there is no snow in the image, you see that the accuracy is very good. But if there is, if the image is taken through a, let's say, snowstorm, the accuracy could drop to 60%. In other words, this transformation is typically called natural variation, and our modern deep learning systems are also fragile with respect to these kind of transformations as well. Now, the geometries that these kind of perturbations have is much more complex than, let's say, L2 or L infinity ball. For example, in the case of adversarial patches, these are also called as sparse perturbations because so we take the image and we just choose a few coordinates to change arbitrarily. So these are sparse changes through the image. And the geometry, and for those of you who are familiar with the compressed sensing literature, here the geometry is the so-called L0 ball, which is non-smooth, non-convex, and unbound. It's quite a difficult geometry to work with for the perturbations. So for the natural variation on the right, the geometry the geometry is even unknown. We don't know what the geometry is. We don't have an analytical model that describes how a snow would be added to an image, right? So it's a manifold, supposedly, but it's unknown and very complex. We don't even know what the geometry is to work with, right? So these are two different types of transformations or geometries that are very important for safety critical applications, and they are much more complex than, let's say, L2. Now, so far, the literature has focused on L2 balls because they are very simple, and you can provide algorithms, you can provide many theoretical results on fundamental limits on these, on these kind of geometries, on the L2 geometries. I call the L2 geometries as a kind of a toy example that we would like to study and understand. And this toy example would basically guide us through other kinds of geometry, more complicated geometries. So also in this talk, I would consider norm-bounded perturbations, again, the simplest geometry. But again, like many other papers, the insights that we obtain from these norm-bounded perturbations are directly applicable to other types of geometries as well. And the talk has two parts. The first part will be about adversarially robust models or adversarial examples. So I'll talk about different frameworks for adversarial examples, how to train models to make them robust against these kind of examples. And also the main part of this, the main content of the first part will be about fundamental limits of robustness or fundamental trade-offs between robustness and accuracy. For the second part, once the first part finishes, we will see that in many cases, the case of adversarially robust models is quite on the conservative side. So we need to maybe relax it a bit. And that brings us to the second part of the talk, which we will talk about, which will be about a new notion of robustness, which we call probabilistically robust models. And then I will talk about whatever fundamental limits here, as well as algorithm design to make our algorithms robust with respect to this new notion of robustness. So these are the two parts of the talk. So if there are questions, I'll be happy to answer them. Otherwise, I'll continue with the first part of the talk. Okay. I guess there are no questions. So the first part of the talk is about adversarial examples. And so in order to re-explain the results, I'd like to dig further into this geometric picture that we had on adversarial examples. To do so, and also to introduce some notation, let me take a step back. Actually, let me go 50 years back and talk about the good old setting of supervised learning. So nothing in this slide will be adversarial. I'll just introduce the setting of supervised learning. So in supervised learning, data which consists of a feature vector X and a label Y, that's the data point. It comes from a distribution D. And the goal of supervised learning is to find a model, let's call it theta star, which minimizes the expected loss. Okay, so given a model theta, the loss function L, here and throughout the talk, the loss function will be represented by L. So which basically the loss function measures the performance of a model theta in predicting the label Y of a data point X. Okay, and in supervised learning, we are searching for a model theta that minimizes the expected loss, and this expectation is over the distribution of the data. Now, in practice, we don't have access to the distribution of the data. Instead, we have n, let's say, data points, which are typically assumed to come IID from this distribution D. And the method of choice here is to basically relax this expectation to the so-called empirical risk minimization objective. Essentially, what we do is that we relax the expectation to the sum over all the training data points. So theta hat that you see here is called the solution to the ERM problem or the ERM objective, which is essentially the best fit to the training data that we have. Okay, so that's theta hat. And this is supervised learning. There has been 50 or 60 years of progress into it. We now have hypothesis classes and models that really work well on test data points that come from the same distribution as the training data. Okay, so in other words, on benign inputs or on clean data points, the solution of ERM works quite well. And as I mentioned before, the solution of ERM fails badly on adversarial examples, on norm-bounded perturbations of the input. So that was.
Can I?
Yeah.
Sorry. Can I ask?
Sure.
I'm not that well versed, so maybe I'm missing something. But let's say you are not ERM, right? Let's say you had an exact statistical risk minimizer.
Mm-hmm.
There's still going to be a decision boundary around which, a small perturbation will take you to the other part. So what makes an adversarial example? Because by very nature, the decision boundary is, decision boundary between two examples. You will take something and you will go to the other side. So
yeah, if you are, well, it depends how far our data point is with respect to the decision boundary, right? So if and this this is the decision boundary is something that we design. So if our data point is quite far from the decision boundary, then it's the ball of radius epsilon. You should think of epsilon to be very small. The ball of radius epsilon doesn't really touch the boundary, right? But for points that are very close to the boundary, whatever boundary we found, the points that are very close to the boundary, they always have adversarial examples.
Right, but I guess I was trying to maybe make a different point, which is that let's say you have a base optimal decision boundary, right? Whatever that base optimal decision is, now you can't improve upon that. That has nothing to do with training example and whatnot. And so around that, is it fair to call it adversarial examples, because around that decision boundary, you will have, perturbation that will take you other. And this has nothing to do with training data. I'm just talking about, the base setup.
Right. So for the base optimal solution is optimal, is the minimizer. So if we are talking in the context of classification, the base optimal solution is the minimizer of the expected loss, the accuracy, right? However, we don't know if it's the minimizer. If it's the best classifier when we have adversarial examples, right? It might be that, it's typically the case that there is a different classifier that minimizes the adversarial risk. Is it clear what I'm saying?
Maybe it will become clear after some of your other thoughts. Sorry, maybe I'm asking very silly questions.
Let me maybe continue. And in
sure,
the objective clear. Okay, thanks for the question. All right, so that was the solution of ERM. As I said, there's nothing adversarial yet here. We just talked about ERM. Now, but the solution of ERM fails badly on adversarial examples. Now, it turns out that if you want to be robust with respect to these adversarial examples, there is a different objective that we have to minimize. And that objective is given as follows. So data still comes from the same distribution, D. However, the loss here is measured differently. So for every data point X, if you look at the formula in the right-hand side, the inner max, for every data point X, we go through a ball of radius epsilon around that point X. So these are all the delta would be the perturbation, its norm is less than epsilon. And we would find the point that maximizes this loss. So we would look at the maximum loss on the ball, among the ball of radius epsilon around each data point X. And that is our new loss function that we have to minimize for every data point, right? And this is the performance of the adversarial example within the ball, this max here. So in the adversarial setting, we need to, if we want to minimize our adversarial error, we need to minimize this objective. So find a model that minimizes the expected maximum loss among a ball of radius epsilon around each data point X. Okay, so that's the objective that we need to solve. Now, again, we don't have access to the distribution D, we only have training data points. So one way, which is the most common way to relax this objective, this statistical objective, is to just relax it to the sum of over the training data points. Okay, so theta hat epsilon, which is the solution of the robust ERM problem, is the model that minimizes this sum over all the data points. And for each data point, essentially, we look at the maximum loss on a ball of radius epsilon around that training data point. Okay, that's the solution of the robust ERM problem. So if I want to explain these two paradigms, the ERM and robust ERM, in one picture, in using a simple illustration, it could be as follows. So let's assume that you have a simple binary classification problem. So data points have two classes, either the yellow class or the blue class. And so ERM essentially finds a boundary that basically separates these two groups, okay, blue and yellow. That's ERM, theta hat. Now, robust ERM, theta hat epsilon, does the following. So around each data point, it first draws a ball of radius epsilon. So these the squares are the balls of radius epsilon. And it tries to find a boundary, classification boundary, that basically does not touch these balls. Okay, in other words, it finds a boundary that touches the least possible number of balls, as you see here. Okay, so that's the solution. That's the difference between these two learning paradigms. One is ERM is designed for clean inputs. Robust ERM is designed for inputs that are perturbed in the worst case manner. So these are the ERM versus robust ERM. So let me quickly recap. So ERM theta hat works well on benign input. It fares badly on adversarial examples. It turns out that in order to make our models robust, we need to solve a different objective. So the robust ERM objective, theta hat epsilon, which is the solution of the robust ERM objective, works better on adversarial examples. However, it's been repeatedly observed that the performance of the robust ERM objective degrades quite a bit compared to the performance of the solution of ERM. So the performance of theta hat epsilon, although being robust, its performance on benign inputs is quite bad. Okay, let me illustrate this using the numbers on the CFAR dataset. Okay, so on the CFAR dataset, if you look at the solution, the performance of the solution of ERM, these are the blue bars that you see here. So it's clean accuracy, but clean accuracy or standard accuracy, we mean just the performance on clean inputs or non-perturbed inputs. Its performance is very good. It's like 94% accuracy, the solution. And it's robust, its adversarial performance on adversarial inputs is close to zero. It's very bad, fails miserably on adversarial examples. Now, the solution of the robust ERM objective, it's quite robust. So it's adversarial accuracy, its performance is around 50%. This means that on 50%, on almost half the training data points, it worked well even on adversarially perturbed data points. However, what's important here is this part. It's the performance of the robust ERM on clean inputs degrades quite significantly compared to the performance of the ERM objective. Okay, so this is around 10% lower in terms of the clean accuracy. So in other words, there seems to be a kind of a trade-off here. And in order to explain this trade-off, I have this two-dimensional plane. On the x-axis, I have the standard error or the clean accuracy. On the y-axis, I have the adversarial error. Now, the solution of ERM theta hat lies somewhere here. It's a standard error or clean accuracy. So its standard error is low, okay, but its adversarial error is high. Okay, it's bad on adversarial examples. And the solution of robust ERM lies somewhere here. Its adversarial error is better. It's more robust to adversarial examples, but this comes at the cost of increasing the standard error and doing badly on non-perturbed inputs. So there seems to be a trade-off here. And in order to gain accuracy, it seems that we need to pay a price in terms of like clean accuracy or robustness in order to gain robustness. So in order to understand these pros and cons of adversarial examples, there are several key questions that we need to answer here. And some of these works that I mentioned on the right have basically considered some of these questions that I mentioned. So the first key answer, the first key question that we need to ask is whether or not there are fundamental trade-offs between robustness and accuracy. So what I mentioned so far was empirical observations that people have had, that there is a kind of a trade-off between the two objectives, robustness and accuracy. However, somebody may come and say that, look, I mean, you observe these trade-offs in practice because maybe your algorithms are not good, or maybe you don't have sufficiently many data points, or maybe whatever, your computational complexity is not enough, and so on. So in order to basically answer this question or see if there is a trade-off, we need to characterize the fundamental trade-offs between robustness and accuracy that hold no matter what our computational power is, what our number of data points is, and so on and so forth. So that's the first question. The second question is, once we have these fundamental trade-offs, how can we algorithmically achieve these trade-offs? And the third question is, what's the role of other factors in this setting, like the size and quality of data, or the model size, or the hypothesis class, or over-parameterization, and so on. So we're going to answer these questions in the context of a problem setting, which is called the Gaussian linear regression. It's one of the simplest settings in machine learning, but yet it's one of the most foundational, central settings in machine learning. And let me quickly explain what linear regression or Gaussian linear regression is. So here we assume that the feature vectors, x's, come from the Gaussian distribution. Okay, so very simple. It's just a Gaussian distribution here for x. And the label y is given by the inner product of the feature vector x times a ground truth vector theta 0 plus some additional noise w. okay? And the additional noise is independent of everything else. That's the linear regression problem where the feature vector has a Gaussian distribution, okay? And theta 0 here typically is called the ground truth model. So given n training data points, the goal of linear regression problem is to basically find this ground truth model theta 0 from data. And we also add an additional adversarial component to the problem, in which we assume that every data point x would be perturbed within a ball of radius epsilon around it. Okay, so that's and the ball is the L2 ball. Of course, the setting could be made more general in terms of the Gaussianity assumptions, as well as the, we can also consider other balls rather than the L2 ball, but just let me be as simple as possible here and consider the most simple setting because the messages are the same. So that's our setting. And let me also define what kind of loss function we are considering. So given a model theta, a choice of parameters theta, the model theta can be used to predict the label associated with the data point x in the following way. So the predicted label by a model theta would be y hat, which is given as the inner product of x and theta. That's just a linear regression problem. And the loss that the model theta incurs in predicting the label of the data point x is given by this quadratic loss. So the difference between, so the square of the difference between the actual label associated with data point x and what the model theta is predicting, right? So that's the loss. Now, once we have the loss, we can define the two concepts, the standard risk and the adversarial risks as follows. So the standard risk is the typical risk of supervised learning, the expected value of the loss for a model theta, and the adversarial risk of a model theta would be the adversarial risk. So the expected value of the maximum loss over the ball of radius epsilon on each data. Okay, so this is essentially the standard error or the clean accuracy. This one is the adversarial error. And we want to understand the trade-off between these two objectives, the standard risk, SR, and the adversarial risk, AR, for the problem of linear regression. Now, in order to characterize this trade-off, our approach has been the following. So let's consider, again, let's consider the same two-dimensional plane that I mentioned. So a standard risk on the x-axis, the adversarial risk on the y-axis. Now, for each model theta, for each possible model for this problem, theta, you can compute the standard risk and the adversarial risk. And that gives you a pair in this two-dimensional plane. Okay, so every model gives you a point in this two-dimensional plane. And once you put all these points together, you will reach to a region, which we call the achievable region. Okay, so this region here is the region of all the achievable points, the standard risk and the pairs of a standard risk and adversarial risk. Now, in order to find these fundamental trade-offs, what's important to characterize for this region is the so-called Pareto boundary of this region. What's the Pareto boundary? These are the points on the boundary, the left bottom boundary of this region. Every Pareto point, every point at this boundary has the following property. That, so consider, for example, this point here, which is a Pareto point. Now, so for every Pareto point, if you want to simultaneously decrease the standard risk as well as the adversarial risk of the point, you would basically fall outside of this achievable region. In other words, for every point on the boundary, for every Pareto point, there is no other point in the region that has a smaller standard risk and a smaller adversarial risk at this point. So these points are really the optimal points of our problem. And understanding how this boundary, this set of points behaves would give us the fundamental trade-off between robustness and accuracy, between the adversarial risk and the standard risk. Now, for the regression problem, the good news is that this achievable region is a convex region. So there is a very simple trick to find the Pareto boundary of this region. It's called the supporting hyperplane trick. Essentially, what we do is that we go over all the lines that are tangent to this region, and the tangent point would give us a Pareto point. Now, there is a very easy way to characterize all the tangent lines. Essentially, we minimize this objective that you see at the bottom of the page. For lambda basically varying from 0 to infinity. So as we vary lambda from 0 to plus infinity, we essentially sweep the Pareto boundary of this region. Okay. The second good news is that this optimization problem that you see at the bottom of the page can be solved in closed form. I mean, there are a few pages of derivations here, but the derivations are not really important. What's important is that we can precisely characterize the Pareto points of this region. And as a result, we can precisely characterize the Pareto boundary of the region or the fundamental trade-offs between adversarial risk and standard risk. So the plot that you see here is an actual plot for a specific linear regression problem that I have provided here of the Pareto boundary. And what's important to again note here is that there is a non-trivial curve here. There's a non-trivial trade-off between the adversarial risk and the standard risk. And this trade-off, this curve here is a fundamental curve. There is no model that could go below this curve. There's no model for this problem. And as you see here, if you want to decrease the best adversarial risk, you will have to increase the standard risk and vice versa. So there is this fundamental trade-off that holds between robustness and accuracy for this problem. As I said, the linear regression problem is one of the simplest yet most foundational problems in machine learning. And even for this very simple problem, you see that there are fundamental tensions or conflicts or trade-offs between robustness and accuracy that you see here. So that was the first result here. If there are questions, I'll be happy to answer. If not, go to the second result, which is about the algorithmic trade-offs for this problem. All right, so let me maybe continue. So now that we have the fundamental limits for this problem, fundamental limits of robustness, the next natural question to ask is whether or not if it's possible to achieve, to get close to these optimal trade-offs algorithmically. And well, I have only talked about one algorithm, which is the robust ERM problem. And as I said, this algorithm is one of the most common algorithms for robust learning. And essentially, the robust ERM problem would basically find a model that minimizes the expected adversarial risk over all the data, the empirical adversarial risk over all the data points. So theta hat epsilon. Now here, I'm going to do something else at training time. I'm going to vary the value of epsilon from 0 to infinity. When epsilon is 0 at training time, this means that at training time, when epsilon is 0, this means that I assume that there is no adversary in the system. So essentially, for epsilon 0, my solution would be the solution of the ERM problem. When epsilon is infinity, this means that I'm giving infinite power to the adversary. So my solution would be would essentially assume that the adversary has infinite epsilon, which is a very bad solution. But by varying epsilon from 0 to infinity, I would get a family of algorithmic solutions to my problem, which are solutions of this robust ERM problem. Now, so let's study the behavior of the solution of the robust ERM problem. So again, what was our setting? Our setting was the Gaussian linear regression problem. The features are Gaussian. The labels are the inner product of the features and a ground truth model theta 0 plus some additional noise. Two important parameters for this problem are the following: n, the number of data points, and p, the number of parameters. And the regime that we study this problem, the solutions of the ERM problem, is the following regime. We assume that the problem is asymptotic in n, the number of data points, so the number of data points goes to infinity. However, the ratio between the number of data points and the number of parameters is fixed. Okay, so here this ratio is typically called the overparameterization ratio. So if this ratio is small, this means that we will have much more parameters than the number of data points. And if the ratio is large, this means that we have much more data points than the number of parameters. Okay, and this is typically the regime that people study the Gaussian linear regression problem for different objectives. Okay, so within this regime, the second result of the talk shows that we can precisely characterize the standard risk and the adversarial risk for the solutions of the robust ERM problem. Now, this characterization is with respect to these parameters that we see: alpha star, theta, whatever, like beta star, tau star, and so on. These are solutions of a four-dimensional like optimization problem that you see at the bottom. I mean, you can show. I mean, the objective itself is not really important.
So wait, if that's a simple problem, I'd hate to see what you call a complex problem.
Simple in the sense that
given that formula.
Simple in the sense that you can numerically optimize it, and it has all the good properties that you expect. So like gradient descent, ascent descent would basically converge to a unique solution of the problem. So we don't need to worry about like non-convexity and so on. So the important thing here is that you can, for every value of epsilon, you can precisely characterize the standard risk and the adversarial risk for the solution of the robust ERM problem in the regime that I mentioned. Now, let me talk about the implications of the results and the resulting plots. So here I've plotted the trade-off curves for different values of the overparameterization parameter. Okay. Now let's look at the curve, the black curve at the bottom left in this plot. So that's the fundamental limit. Okay. So we cannot do better than this fundamental limit. It's basically the optimal trade-off that we can have. Now, what we see here is that as the number of as the overparameterization parameter goes to 0, this means that the number of data points, as the number of data points becomes much larger than the number of parameters, or the trade-off curves for the algorithmic solutions get closer and closer to the optimal trade-off. This means that this robust ERM problem becomes basically gets very close to the fundamental limit in the case where the number of data points, training data points, is much larger than the number of parameters. Or in other words, in the case where the problem is in this under-parameterized regime. Also, at the same time, we will see that we are seeing that if the problem is over-parameterized, meaning that if you have more parameters than the number of training data points, the trade-off curve gets further and further away from the optimal trade-off. So this means that more over-parameterization for this problem is hurting. It's hurting even the standard accuracy and the adversarial accuracy. So for these kind of problems, adversarial problems, over-parameterization actually hurts the performance, the robustness, and also the trade-off between robustness and accuracy. Now, why is this important? Because in the non-robust setting, when we have no adversarial examples, it's known that over-parameterized models are useful. They're good in the sense that, so that people have been talking about this double descent phenomenon, that they have been proving its benefits in various aspects. For example, people have shown that, for example, more over-parameterization would give you a better optimization landscape. It gives you easier optimization algorithms. It also gives you better solutions in terms of the standard error and so on. However, what we are seeing here is that these kind of interesting phenomenon properties do not really hold in the adversarial setting. Somehow more over-parameterization is essentially hurting our robustness, as we see. So that brings me to the end of the first part of the talk. So let me just do a quick summary here. So we talked about the robust, so adversarial examples and the solutions of the robust ERM problem. And we basically we showed that there are fundamental trade-offs between robustness and accuracies for this problem. We talked about algorithmic trade-offs, and we showed that for at least for the case of linear regression, there is this curse of over-parameterization for this problem. As the models become more and more over-parameterized, the robustness would be so the problem would over-parameterization essentially would hurt the performance in terms of robustness and accuracy. Now, so I have around like 10 minutes or so. So let me go to the second part of the talk, which essentially shows that we can consider new notions of robustness, maybe slightly less conservative notions of robustness, and we can essentially get rid of these trade-offs that I've been talking about. Okay, and these new notions of robustness would be useful, let's say, for the practical or safety critical applications that we have been considering. The main point to consider here is that these adversarial examples are way too conservative in the sense that we draw a ball of radius epsilon and we want for every point within the ball to be classified correctly. let's see if we can slightly relax this requirement for adversarial examples. So essentially what we want to do here in the second part of the talk is an interpolation or a balancing between the average and worst case kind of performance within these balls around the data points. Okay, so the core idea comes from this famous observation that people have had in the context of robust machine learning. The observation is as follows. Typically, if you consider a data point, if you consider the ball of radius epsilon around this data point, then adversarial examples would exist in the ball. Okay, there are a few points within the ball that are adversarial examples, which can cause misclassification. However, adversarial examples are very rare. Or in other words, the portion of the points within the ball that are adversarial examples is very small, that portion. Okay, so if, for example, if you required, so for example, if you typically the ratio of adversarial examples is around like whatever, like maybe less than 5% or even 1% of the ball, if you consider the uniform measure and so on. Okay, so that's the main observation. Typically, adversarial examples are in a very narrow strip inside the ball of radius epsilon. And this has been investigated in several papers, both theoretically and also numerically. So, given this observation, a way to relax this worst case notion of robustness would be as follows. So adversarial robustness would require that given a ball of radius epsilon, we have to correctly classify all the points in that ball. Otherwise, there would be an adversarial example. We can relax this word all to, let's say, almost all or most of the points. Okay, so and this gives us this new notion of probabilistic robustness. So instead of requiring that all the classifier classifies all the points, we would require the classifier to correctly classify, let's say, a good fraction of the points. Let's say 99% of the points within the ball. And if you think about our safety critical applications, that's typically what we need, right? So we want to be robust 99% of the time, and you can improve that. So you want to be robust, let's say 0.999% of the times. And this is somehow similar to, I mean, as the audience has a lot of information theories, this is similar to error correcting codes when, so I mean, obtaining worst case results is very difficult in error correcting codes, but average case, we can always decrease the, let's say, average probability of error using codes. But the worst case is typically very hard to minimize, and we get a
do you when you say probabilistic, are you going to say randomly select the set which is the bad set then, or are you? I mean, so
according to some probability distribution, yes.
Okay.
Yes. Okay. So, for example, if you put uniform measure on the ball, then the probability of finding, let's say, an adversarial example would be for that specific classifier would be, let's say, less than 1%. Okay, so that's somehow an intuitive picture of how we can define probabilistic robustness. Of course, there are several key questions. I mean, this is nice, but how can we formally define probabilistic robustness? That's question number one. Once we've found a mathematical characterization of that, there are fundamental limits or fundamental questions to be answered. Another question is whether or not there are fundamental benefits of basically defining such a new notion of robustness compared to, let's say, worst case or adversarial robustness. And finally, can we design efficient algorithms that make our models robust with respect to this new notion of robustness? So these are the key questions that we need to answer regarding this kind of observation or this notion of probabilistic robustness. Let me try to maybe answer these questions here for the remaining, let's say, 5 minutes or so. All right, so probabilistic robust learning, I mean, if I want to put pictorially describe it, so we want to find a classification boundary that it might hit some of the balls, some of these balls of radius epsilon on the data points, but the portion of the ball that would reside on the other side of the boundary would be very small. Okay, would be smaller than, let's say, 1%, or a given value rho. okay, given threshold rho. Okay, so that's basically the picture that we are talking about. The core idea, as I mentioned before, is to enforce robustness to most, but not all the perturbations. Well, when we talk about most, we need to have a measure. We need to have a way of quantifying what we mean by a fraction of the points, and that requires a probability distribution. So if you let delta to be the neighborhood around the data point that you want to enforce robustness, then we need to also consider probability distribution. Let's call it Q on this neighborhood. Yeah, I mean, in simpler settings like adversarial examples or normal perturbation, you can think of Q to be the uniform distribution on the ball, for example. Okay, so we work with a distribution Q on the neighborhood, and we assume that this Q is given or is defined. And let's see what the objective is that we have to solve in order to basically define robustness with respect to these kind of notions of robustness. Now, this minimax objective that you see here is the objective that basically represents adversarial robustness. So the inner max that you see here is the max of the loss value over the neighborhood delta around the data point. So this is just the adversarial or the worst case setting. Now, let's just start from here and see how we can reach this notion of probabilistic robustness. So, I mean, there are various ways to write this. I'll try to one way, which essentially in the end gives us this notion of a rho essential soup for this problem. So we would basically change max to essential max or essential supremum, and so this depends on this value rho, this threshold rho that we have been talking about. So let's rewrite max in the following way. If you look at the optimization problem on the right, it's another way to basically characterize the value of the max of the loss function in the neighborhood delta around each data point. Now, so what we want, remember, what we want is that we want a notion of robustness that applies to a fraction, let's say 1 minus rho of the data points in the neighborhood, but not all, okay? So one way to define this notion of robustness is as follows. So we would look for the data point X, and rho is a given threshold of the problem. Think of rho as 0.01, right? So we want to have 99% robustness within the neighborhood. So US star that you see here is the smallest value such that the fraction of the fraction of the values of the loss function in the neighborhood that are above this value US star is at least 1 minus rho. Okay, so in other words, US star is the value such that a fraction 1 minus rho of the points in the neighborhood are less than this US star. They're good. So if I want to, and that's essentially the definition of the rho essential soup as we see here. So I have a plot that makes it easier to explain here. So let me maybe skip these definitions. So on the x-axis, assume that I have the neighborhood delta, the ball of radius epsilon. Okay. Now the soup over all the loss values is somewhere here. So this point here in the neighborhood would give you the adversarial example, would give you the maximum loss value. Now, so this is the expected loss over the neighborhood according to the distribution Q. The rho essential soup is the smallest value that we can have. Look at the green line here, such that the fraction of points in the neighborhood that value above this green line is less than rho. Okay, and that's the definition of the rho essential soup. So that's the notion that we want to minimize here for our data points. Okay, because these points whose value is above this rho essential soup, these are problematic points, and we want to basically minimize the loss basically associated with these points.
Can I interpret this as like a typicality thing? Like this is like atypical losses. You want to minimize the area of the atypical losses.
Yes. So we are given an area. Let's call it rho.
Right.
Right. So we are given the area. So I mean the atypical loss. So what we want is the following. So given the neighborhood, I'm allowed to throw away a fraction row of the points in the neighborhood. Whatever their loss is, I don't care.
Right.
What's important for me is to be good on this 1 minus row, like the fraction 1 minus row of the other points. Now, the maximum loss for those other points is this row essential soup.
Okay.
Okay. And of course, the objective that I need to minimize is essentially for every data point is this row essential soup that you see here. Okay, let me, okay, these are simple properties of row essential. So essentially, this is the objective that I want to minimize. So for every point X, I go over this ball or neighborhood around this point X, and I look at, so I'm given a row, I look at the row essential soup, and I want to minimize that. Okay. Now,
I have a question.
Yeah,
I have a question if you don't mind. So,
sure.
What if the area you're throwing out has like multiple neighborhoods? Do you double count them or no?
Multiple. So your voice was cut for a second. So
So for example, if you throw away only a portion of your neighborhoods, right? What if that neighborhood was in other data's neighborhood? Do you double count those areas?
Yeah, you double. So you want this to hold for every data. So you would double count this. So this, okay. So inside this expectation. So here X is fixed, right? The data point is fixed, and you want to enforce this for that specific data point and the neighborhood for that specific data point. For a different data point, it's a different story, and you have to compute the row essential soup separately.
Okay, thank you.
Okay, thanks. And that's the same case for adversarial examples. Think about it. Okay, so so playing with this value row essentially would give you an interpolation between the adversarial examples. So if row is 0, think about it again. If row is 0, we are on the soup basically, right? And if row is 1, we are on the average case. So changing row from 0 to 1 gives you an interpolation between the average case or ERM and the adversarial case. And also this is interpretable because row is essentially the fraction in the neighborhood that you want to be robust against. Okay, so these are the two properties of this notion of robustness that we are introducing here. Now, how to optimize this? Of course, this objective here is very complicated. It's non-smooth, non-convex, and so on. There is a tight relaxation of it. It's called the CVAR objective. So the CVAR objective or the CVAR relaxation has been used quite a bit in risk-sensitive ML, risk-sensitive reinforcement learning, and other risk-sensitive control, and so on. And it's also useful for us here. It's an upper bounds and relaxation, but it's amenable to optimization. So instead of row essential soup, which is intractable to optimize, we consider the CVAR objective to optimize, and that's a relaxation. I mean, I'm talking about the algorithms to basically find a model that's robust according to this notion. And well, once we have the CVAR, I mean, there is the tractability here that we can have, and then we can basically design an algorithm, a kind of similar to a minimax optimization algorithm, but in the inner objective, you have the CVAR objective. So you can design again a kind of a robust ERM objective to basically solve this the CVAR objective that I mentioned. Now, I know I'm out of time, but just let me explain the numerical results that we get, because there is an important point here that I want to explain. So let's look at the numerical results. So we formulate this CVAR objective, we minimize it, we find a model, and we measure the robustness of this model according to the notion that we have. Now, here on the last column, this is for row equals 0, row being 0.01. This means that we need 99% accuracy on the ball. You see that, first of all, PRL is the algorithm that I mentioned based on CVAR. It has the highest robustness compared to all the baselines for robustness. I mean, PGD trades, these are all different algorithms. And there is ERM here, which has less robustness. But what's important here, what's important here is to look at the clean accuracy also. So if you look at the clean accuracy, that's the performance on non-perturb or benign inputs. The clean accuracy of this algorithm is very close to the clean accuracy of ERM, to the best clean accuracy that you can have. So as you see here, while these algorithms are being robust, their clean accuracy does not degrade with respect to ERM. So this trade-off that we have been talking about in the first part that we talked about, this trade-off essentially is mitigated, as you see here, or essentially does not exist. And this can be provably shown. So in the setting of the Gaussian linear regression problem that I mentioned in the first part of the talk, you can show that the gap between robustness and accuracy shrinks as something of order 1/√d, where d is the dimension. So if the model or your data is high dimensional, essentially the trade-off vanishes as the dimension grows. Okay, let me actually stop here. What's important, okay, let me go to the summary slide. So for the second part, we define this notion of robustness, new notion of robustness, which is a probabilistic version of robustness. And we showed that essentially that these trade-offs that existed before does not really basically hold in this case as the dimension of the model grows. Okay, thank you.